multiple bonds. And how do I work in multiple bonds with hybrid orbitals and valence bond theory? Well, let's recall first of all that multiple bonds are formed with two types of overlaps. You have sigmas and you have pi's. That's it. That's all we need. We don't need any more than that. And we already said that what's always true is that a single bond is going to be a sigma overlap. A double bond is a one sigma and one pi. There's two bonds, double bond, and a triple bond is going to have one sigma and then two pi's that overlap it like that. And so that's the kind of overlap that I'm looking for. And previously we discussed this in terms of atomic orbitals. So like a p and a p could overlap to give you a pi type of bond, or an s and an s could overlap to give you a sigma type of a bond. But you know what? This works with hybrid orbitals just fine as well. We can overlap them and get the same sort of covalent bonds. And what we're going to find is that the sigma bonds result from the overlap of either hybrid or pure atomic orbitals. We get a single region of overlap, so it's a sigma. The pi bonds almost always are formed by the overlap of the atomic p orbitals that are left over, the ones that were not used in the hybridization. They overlap top to bottom like this in those two regions to give you a pi type of a bond, which is either the second or the third in either a double or a triple bond. Alright, so to see this in action, let's look at the molecule C2H4. C2H4, if you do its electron dot structure, you're going to get this right here. I'm not going to go through the counting of the electrons. This is what you'll get. You have a double bond between the two carbons and then single bonds going out this way. Now I can already count how many sigmas and pi's, right? I've got 1, 2, 3, 4 sigmas, and then a fifth one is this double bond and 1 pi. And so I know what type of overlaps I have. Also, I know the geometries. If I look at this carbon here, there are three things coming off of it. Right? A single, and a double. That means it's trigonal planar, which means it has an sp2 hybrid. Same thing with this carbon over here. So I know what the hybridizations are. I know what the shapes, I should say the electron geometries are around each one of those. Right? Now, how do I actually describe this using sigmas and pi's given the fact that I've got sp2 hybridizations? Alright, let's think about the energy levels. Here I've got my carbon, and I've got my 1s level, my 2s, my 2p's for carbon. And actually, if I filled it up, carbon is a 2p2, and so they didn't ask to put this in, but just to show you, one up, one down, one up, one down, up, and there we go. That would be carbon. I'm not using this p orbital here at all, but there's the 6 electrons for carbon. Now what I'm going to do is form the hybrids though, because this carbon doesn't keep those. This carbon goes into sp2 hybrids. In other words, it takes its s and it takes 2 of the p's, hybridizes them together to an equal energy, this case threefold degenerate hybrid atomic orbitals. All right, and so I've indicated this with my red circles and arrows here. The 1s is still a 1s looking like that. All right. And yeah, it's still got its 2 there. Then I take my 2s and a p and another p. Now there's sp2 hybrids, right? So here's the s, here's the first p, and there's the second p. I hybridize those together to give me sp2 hybrids, and there are 3 of them, which is why I've got the 3 lines here. Remember, they're all the same energy. And the electrons, look at, there's another 1, 2, 3, 4 type electrons that would be going into those, if you will. And then I've got my leftover one right here that was not used. So there's the 2p up here not being used. So if I was to fill in my electrons on that, it would look something like that. Okay, ready to bond and in the right geometries. Now these electrons will change their energy levels a little bit as I make the bond, but I just wanted to show you how they would fall into place. The important thing is to see that over here are my atomic orbitals, and then over here are my hybrid atomic orbitals. These are the ones that we usually think of with just a single atom. This is the one now that is in the correct geometry to create that molecule right there with an sp2 hybrid and a trigonal planar geometry right there. Okay. This leftover p orbital right here is the one that's going to be responsible for creating the pi type overlap. Where these sp2s right here, 1, 2, 3 of them in the 1, 2, 3 directions of a trigonal planar, those are the ones that are going to create my sigma type overlaps. If I've got both of those present at the same time, a sigma and a pi, hey, that's a double bond, and that's exactly what I'm going for. Alright, so if I scroll down a little bit here, here's an excellent picture showing how this actually looks. Here's my left carbon right there and my right carbon. You can see in the yellow orangish ones here, these are my hybrid orbitals. So these are my sp2. I got an sp2 and an sp2. Right. And they don't actually label those, but this is it right there. That's an sp2 hybrid, and so is that one, and so is that one. Those are all sp2 hybrids. Here, going up and down, is my leftover p orbital right there, the one that I did not use to create the hybrids. And so I'm seeing how all that is surrounding that carbon atom. Now going out to the hydrogen, hydrogen has just a 1s orbital. I didn't create any hybrids with those. I just am doing the hybridization in the central atom to look at the geometry of that molecule. But you see here, if I bring that 1s from the hydrogen and then the sp2 of the carbon, that'll overlap in a sigma bond. And that would correspond then to, like this guy right here, where I am making a single bond between the carbon and the hydrogen. I do the same thing with this other one, and then this one here goes in here and creates the first of the double bond going to the second carbon. The right carbon's doing the same kind of a thing. So from one carbon right here, this first carbon here, going to the second carbon here, so far I've got a single bond. That single bond is made of that sigma overlap of my sp2 hybrid from the left and my sp2 hybrid from the right. Then my leftover p's, which I haven't talked about yet, up and down here, they will also overlap as I bring them close together, and they overlap in these two different regions, so that's a pi. Here's the picture of that. They're showing, here's my first region up in the top, my second region down here in the bottom. Just because it's split into two different regions, keep in mind that's still just a bond. It's not two bonds, it's just a bond. Okay, but it's a style of overlap. It's a pi overlap as opposed to a sigma. All right, so I've got my first of my two bonds of my double bond here with the sigma, and then here's my second with the pi bond that forms. So here's my one bond, and then here is half, and then the other half of my second bond. And so this is a double bond actually, a sigma and a pi, forming a double bond between those two carbons. Okay. If I was to do a triple bond, it would look very similar to this, except I wouldn't have just a single p orbital that's left over. I'd have two p orbitals, and they'd be at 90 degrees. So one's going here, one's going here, and I would get an overlap region this way and an overlap region this way, and I could get the sigma right in the middle, and then a pi, and then another pi, for a grand total of 3 overlaps, 3 different bonds, and therefore a triple bond. Alright, so let's do one example here, SO2, to show the resonance and the type of hybridization that we have here. Alright, so sulfur has 6 electrons, my 2 oxygens, that's another 12, there's no charge, so this is a fairly easy one, just 18 electrons. So I have my sulfur, my oxygen, if I give everything an octet, and then see how many I've used, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Whoops, I've used too many, and so I take off a lone pair, make that into a double bond instead. That drops me to 18. This looks good. And so there's my, a little sloppy, but my Lewis electron dot structure for SO2. I've got, as you can see, a double bond going to the left and a single bond going to the right. Of course, I didn't have to choose left. I could have gone to the right with that double bond, and so I do have a resonance form which would look like that. And so I would have to draw them both to correctly show my Lewis electron dot structure for SO2. Now what about the hybridization? Well, that sulfur has 3 different things coming off of it. It has a double bond, a single bond, and a lone pair. And so those sulfurs are trigonal planar, 3 things coming off, which means they are sp2 hybrids. Over here I have a sigma and a pi bond to make my double bond. Over on the right side I've got just a sigma. Now, of course, with the resonance structures, we lose a little bit of that because the electrons are not being held just between, say, like that sulfur and that oxygen. With a resonance forms, hey, sometimes that second bond is over on the right side, sometimes it's over on the left side, like I've shown up here. They are what's called delocalized. Delocalized electrons occur when you have resonance forms like this, and those electrons spread themselves around. Remember, they're waves and they have a particular shape, so they spread themselves around across both positions of that bond. And so in this case, I can describe it as the sigmas and pi's and sp2 hybrids, but a better description would be, say, I've got delocalized electrons, and not that I have a single and a double bond, but that I actually have a 1 1/2 bond in each case. And that's harder to draw. I would have to do something like this. I've got my single and then maybe like a half bond here and a half bond there, that kind of an idea. So 1 1/2 bonds. Of course, you could count that and come up with that bond order fairly easily, because if you see the electrons involved, I've got this bond, which is a single, and then a double, so that's a grand total of 3 bonds, and I'm distributing them in 2 positions, to the left and to the right. So 3 over 2, yep, sure enough, that's a 1 1/2 order. So it's not like I've got single or doubles, but I've actually got a 1 1/2 bond between each side of that molecule. Right. But that fully describes the more advanced way of thinking about these covalent bonds.